Alright, in this video we're going to do one example of IS slides, one example on paper, and then you guys will have a practice problem that I will show the solution to at the end. Just using the ideal gas law and some of these gas concepts to solve stoichiometric related problems. So we have a chemical reaction going on in all of these. So methane burns in oxygen to form carbon dioxide and water. Remember that the coefficients also can correspond to the volume equivalents if temperature and pressure are constant. So the question is, if 4.5 liters of methane burns in air, how much oxygen is consumed? And it asks for volume in liters. And then it tells us, oh, both of these are at STP, so we don't have to worry about pressure or temperature. So we're just going to look at the stoichiometric coefficients and use those ratios as if they're volumes. So what we're going to do is take the volume of methane and then multiply by the stoichiometric ratio, 2 liters of oxygen to 1 liter of methane. And when we multiply 4.5 times 2, we get 9.00. And we do get 3 significant digits because stoichiometric ratios are exact. And that's the answer. Alright, second example. In one lab, the gas collecting apparatus used in a gas bulb, probably glass, but gas bulb, with a volume of 250 milliliters. How many grams of sodium carbonate would be needed to prepare enough carbon dioxide to fill this bulb when the pressure is at 738 torr and the temperature is 23 degrees Celsius? Here's a chemical equation. So what's going on in this problem is that we have some sample of sodium carbonate. We add drops of acid to it. HCl. You get that baking soda and vinegar type reaction. Lots of bubbles. And then above this reaction, sealed in such a way that we don't lose the gas. As this bubbles up, we have it sealed in some container. So maybe we turned the carbon dioxide over. Sorry, this isn't very bulbous. Here's my gas bulb. Yay! So up here we've collected carbon dioxide. Often this will be done where this is filled with water and inverted into the reaction vessel so that we can see when the air starts to fill at the top and it fills the whole bulb. Anyway, so that's the picture. Basically, we're given some information about carbon dioxide that is produced, and we're asked to then find how many grams of sodium carbonate must have originally reacted. So I'm going to do this on paper. Since there's a few steps, I've kept the reaction here. So we have sodium carbonate plus HCl yielding our products. Let's just write out some of the stuff from the problem. All of our information is pretty much about carbon dioxide. We're given its volume, its pressure, its temperature. Let's convert the temperature to Kelvin, since we know we have to do that right away. We get 296.15 Kelvin. 3 significant digits because we keep the ones place. Just labeling my variables, volume, pressure, and temperature. And those are going to end up going into the ideal gas law to solve for moles N of CO2. We also have to convert the volume that's given in milliliters. 1 liter times 1 liter over 1,000 milliliters equals 0.250 liters. So let's plug in our pressure, 738 torr, into the equation. What we're trying to solve for is moles, so that we can go back and calculate moles of sodium carbonate with stoichiometry. So let's plug in our pressure, 738 torr. Now our volume, 0.250 liters, and that's equal to moles times R, 0.08206. And I always write the units for R so that I can make sure I have the correct units in my pressure, volume, and temperature. So actually I just noticed that my atmospheres and my torr are not correct. They don't match. So let's just put that conversion factor here to the left to convert it to atmosphere. Now let's put in temperature, and we plugged in everything to our Pevnert equation. So let's get that new pressure, or I guess convert it. It's not new, it's the same pressure, just in different units. It's 0.971 atmospheres. I kept some extra digits so I didn't get round off error. Multiply that by volume, 0.250 liters, and then divide by R and T to isolate N on the right side. So N will end up equaling 0.00998 something moles of carbon dioxide produced from our acid-base reaction. So now we've got our stoichiometric factor. It happens to be 1:1 in this case. And so our moles of sodium carbonate will be equal to our moles of carbon dioxide. So let's just write that down. No need to write it out. Keep some of those extra digits for moles. Sig figs real quick. We have 3 from a lot of our measurements, so just kind of keep track before we move forward too far and forget what we're doing. Molar mass of sodium carbonate. There's 2 sodiums, 1 carbon, and 3 oxygens. So when we add those up, we'll get a molar mass of 105.99 grams per mole. So if you want to refer to the question again, run back to about the 2 or 3 minute time stamp. But what we're asked for in it, just as a refresher, is grams of sodium carbonate. So right now we have molar mass and moles. Mass is going to equal moles times molar mass, which is 0.0099894 moles times 105.99 grams per mole. Moles cancel, and I'll get my answer in grams. So plug that into my calculator, and I get 1.0587 grams of sodium carbonate. There's 3 sig figs in my moles, so I keep 3 sig figs for an answer that is 1.06 grams. So we're just taking stoichiometry and we're applying it to gas laws. Now we can do some different calculations after we've done stoichiometry, or before, as the case may be. Alright, so now we have solid sodium metal dropped in water. It'll be reactive, it bubbles around a little bit. We can actually watch hydrogen gas evolving. And it produces aqueous sodium hydroxide. And so this is a chance for you to practice with the safety net of the answer coming up in a few minutes. But we're asked how many grams of sodium are required to produce 20 liters of hydrogen gas at this given temperature and pressure. You're going to be using PV equals nRT. And I will pause for a few seconds in case you need time to pause the video. Once you solve for moles of hydrogen, then you do the stoichiometric part and multiply by 2, and then you convert it to grams. So I'm going to show the answer here if you're ready for it. If you got E 37.1 grams, that is correct. And here is a slide that has the work shown in case you need to double check your work at any step. We had to convert the pressure to atmospheres and the temperature to Kelvin so that it lines up with the units that we use for the most common R value. And then once we get moles of hydrogen, we use stoichiometry and the molar mass to get to grams. Alright, so this doesn't complete 9.3 as a section, but this is basically kind of where we'll sit for Thursday. We'll talk about partial pressure and mole fractions and kinetic molecular theory and all of that good stuff, and non-ideal gas behavior on Tuesday. So this is very calculation heavy. There will be some calculations coming up in the last half of the chapter, but part of it is a little conceptual too. So, I'll see you in class.